Well, hello guys, here Mr. G with the second part of the test about work, energy and power. This time, as I said before, we are going to do questions 3 and 4. Previously we answered question 2 and question 1, which was a multiple choice. But before we start, please remember to subscribe for the channel so you can get the notifications and all the worksheets and all the videos I posted on regular basis. Now question 3 say a crate of met 30 kg is placed at the point A on a rough inclined plane. So there is friction in this plane. It's a incline and there is friction. Friction is different than a 0. That makes an angle of 25 degrees with the horizontal. You can see the angle there. The crate slides down from rest. So the speed right here is going to be equal to 0 meters per second, and the object is moving down the incline. This is moving down the incline and travel a distance of d. You don't know d before it reaches the bottom point B with a speed of 2 meters per second. The speed here is equal to 2 meters per second. The crate experiences a constant frictional force of 100 Newton, and there is the frictional force. So it's equal to 0 and equal to, let's write it here, equal to 100 Newton, sliding down from point A. Question 3.1, draw a free body diagram to show all the forces acting on the blow while it moves from the position A to B. And if you go here to question 2, if you did watch, you can see we have a similar free body diagram, but in this case the object was moving up and now the object is moving down, all the way down. So to do this, we are going to do as usual 2 free body diagrams, one for us to understand the question and the other one to answer this question 3.1. So here on the right side, I'm going to answer the one that we always use to complete and understand the question, and on the left we'll answer the free body diagram for the question. Now here, as always, we're going to have the surface. Remember, the surface must be or the x-axis must be parallel to the surface. I'm going to write here displacement because of the use of the work later on. This one is perpendicular to the x-axis, this one is the y-axis. There is the object, and the forces that are acting are frictional force all the way backward. This one is a frictional force. We have normal perpendicular to the surface. Be careful with the normal, guys. People attempt to get confused there. And then finally we have the weight all the way straight down, and this one is the free body diagram. Now in this free body diagram, if you want, because it's just for us to work, and this is only if you want, you can include the components or you can wait for the time when you may need it. This is the component of the weight in the y-axis, and here will be the component of the weight in the x-axis. Note, this one I recommend you to leave it for later on when we need the, if we need it. Otherwise you can leave it out. This angle here is 25 degrees. Remember that one. And also to recall, even before we carry on, this here will be the angle of the pardon, not that one because it's moving down. This angle here will be the angle of the displacement and the gravitational force. And as you can see there, that one will be 90 minus 25. This one is for later on. This is the angle between the gravitational force and the displacement. And the angle between displacement and frictional force, you all know, but it's going to be this one here, which is 180 degrees. So guys, this is the free body diagram, not for mark. We are going to now do the one that they want us to do for marks. And that is quite simple, will be the forces. What forces we have there? The frictional force backward or up the incline. This is frictional force. There is perpendicular to the surface, in other words, will be perpendicular to the frictional force. We have the normal, and straight down we have the weight, and this one is the free body diagram they want for question 3.1. That one there. So I hope you understand. This one here is question 3.1. Okay, question 3.2, state the work energy theorem in words, and we say that one many times. We are going again to go to the formulas, and here we have the work energy theorem. Remember, in the previous video I told you to mark it because it was needed, and all you have to do is to be able to state or translate this one into words. And here is the work energy theorem. We're going to do it here to save and it be clear. So this is the formula, guys. This is the formula you have. And this law states that net work, this is just the translation there of an object, is equal to the object's kinetic energy. No, change in kinetic energy. Let's fix that one. The object's change in kinetic energy. Now it is correct. The net work, saying again, that one object is equal to the object's change in kinetic energy, and the formula is there. It is in the formulas that you are going to get in the exam, guys. So please just remember it is there. All you have to do is to remember that is there, and it's going to be under the section for work, energy and power, and it's going to be always in the same place. So that's all you have to remember. But we now continue with the question. Now question 3.3 said, use the work energy theorem to find the distance d the crate travel from A to B. So we have to use the work energy theorem. Is no other option. We cannot use the law of conservation of energy because they ask us to use this specific theorem. However, I recommend you to do it. The same question, do it with the law of conservation of energy, so you practice the work. So question 3.3. Now question 3.3, they said we must use the work energy theorem, and then we must start with that one. Net work is equal to the change in kinetic energy, and we're going to copy here the free body diagram. And now in the free body diagram, remember we have these forces. These are the forces. The other ones are components. We are going to work with the forces. Those are the three forces. So the net work will be the work done by the frictional force plus the work done by the normal force plus the work done by weight, and that will be equal to half mass multiplied by final speed square minus half mass multiplied by the initial speed square. All right, now you remember we're starting from 0, so the initial speed is going to be 0 as well as all that because it's the product. And then the work done by normal, you're supposed to know by now that in this case is also 0. Remember I said once, it's not always going to be 0. And then the work done by friction, here is going to be equal to a frictional force, which we have it multiplied by the displacement, which we don't have, multiplied by the cosine of theta. And if you go to the free body diagram, we already selected is 180 degrees. If you want, we can substitute here. However, remember we don't have the displacement, but we have the frictional force, which was 100. So it's 100 multiplied by the displacement multiplied by the cosine of 180. And if you carry on, you have that this one will be minus 100 multiplied by displacement. So we have here, this one is the work done by the friction that we are going to substitute in when we finish. The work done by weight is the same story. We're going to go here and substitute. Work done by the weight is equal to the weight multiplied by displacement. We don't have it, we are looking for it, multiplied by the cosine of 90 minus 25. We explained just now that one. And that one is a 65 degree. And then if we carry on, we have this one is mass multiplied by acceleration due to gravity multiplied by displacement, which we don't know, cosine of 65 degree. And when you substitute everything here, you have that is 30 multiplied by 9,8 multiplied by the displacement multiplied by the cosine of 65. The 294 multiplied by cosine of 65 is going to give us 124,25 multiplied by the displacement, and guys, this is what we are going to substitute by the weight done, by the work done by weight. So when we substitute everything in here, what we are going to have? Yes, 124, not 29. I think I say it, I just write it wrong. 124. 124. 24,25 delta x equal to half multiplied by 30 multiplied by 4, or 2 to the power 2. Let's substitute 2 squared. Okay guys, and here we are. Now when we calculate this one, we are going to have that on this left hand side is 24,25 delta x, and on the other side we are going to have 60 when you calculate it. Therefore the displacement is going to be 2,47 meters, and this is the end of this question. This question was quite simple, and that is the answer for the displacement of the object. I hope it's clear. We've done many videos with questions similar to this one, or even I'm not sure if we did the same question before. Question 4 state, we're going to start with question 4 now. I hope you understand question 3. Question 4 state a 2,4 times 10 to the 2 Newton force F applied at an angle of 20 degrees above the horizontal pulls a 85 kilogram block over a distance of 8 meters on a rough horizontal floor as shown in the diagram below. And now here the floor is rough, is important. The distance is 8 meters and the angle between the horizontal and the force is 20 degrees. All the data are here. The only data that we don't have, we are going to add here, is the force is 2,4 times 10 to the 2 Newton. That is the force. Is very much the same force, it's just at different moments. So this one is times 10 to the 2 Newton according to the data they give us. The coefficient of kinetic friction between the floor surface and the block is 0,2. This is coefficient of kinetic friction. 0,2 is very important. And then define a non-conservative force. Please, we spoke about that one, but we are going to write the definition of a non-conservative force. In the previous video, we spoke about that, and as well as we spoke about the example. And here we are. A non-conservative force is a force for which the work done in moving an object between 2 points depend on the path taken. So that is important. The work done in moving an object by that force depend on the path taken. Okay, and we learn about the conservative forces in the previous videos. Please, you can go and watch that one there. So going back to the question, they say calculate the work done by the pulling force. Very easy. We can do it on this side here. If we quickly do the free body diagram real fast on this side here, we don't have to take too long or too big space because we've done this one many times. And now we have that the applied force is going to be in this direction, which make an angle to the displacement. This x is the displacement. You can see this is the angle between the applied force and the displacement, which is 20 degrees in this case. You can see it there. What other forces are acting here? There is also normal force pointing up, there is weight pointing down, and there is frictional force to the back. So this one, guys, is the free body diagram, and remember, I always recommend you to do it because you may need it. So now the question here was to calculate the work done by the applied force, and that is equal to the applied force multiplied by the displacement multiplied by the cosine of 20 degrees, which is the angle in this case. When you substitute, you have is going to be 1804 joules, and this is the answer for that work done by the pulling force, which is this question here. I hope you understand. It's very, very simple. Now, calculate the work done by the frictional force is not a big problem. The only thing is that we don't have the friction, so we have to first of all calculate the friction. For this one, we are most definitely going to a new page, and we're going to take the free body diagram with us. Now, what we need to do, we are asking, or we've been asked to calculate the work done by the frictional force, which is equal to frictional force multiplied by the displacement multiplied by the cosine of 180 degrees. We have that angle there. Now, the issue here is actually that we don't know how to calculate. We don't have the frictional force. We know how to calculate it. Frictional force is equal to the kinetic coefficient of friction multiplied by normal, but they is still having issues here. We don't know the normal, so we do have to go and calculate the normal force. Now, to calculate the normal force, we're going to apply Newton's first law in the y-axis. Now, what do we have in the y-axis? Here is the free body diagram, and then we are going to project the applied force, which is in none of the axes, to each axis there. Let's take off this yellow mark there so you can see better. And then I'm projecting this force to x, and I will have here, this is the applied force in the x-axis, which is not needed right now at the moment. And here, if you project it to the y, you have here the red one, guys. This is the applied force in the y-axis, which is equal to applied force multiplied by sin of 20 degrees. So this is the applied force in the y-axis. Now, what forces do we have in the y-axis? Well, here are the forces we have in the y-axis, and therefore those are the forces we are going to substitute. We have that net force is equal to 0. You don't have to start from here if you don't want to. And then we have the normal plus the applied force in the y-axis is going to be equal to weight. And then if you rearrange or substitute to calculate the normal, you'll get the normal is equal to weight minus the applied force in y-axis. And if you carry on, this is mass multiplied by acceleration due to gravity multiplied by applied force sin theta. And now we are ready to substitute the actual values and calculate what they ask us to calculate here. And then here we go for the normal 747.49. Guys, as I'm talking to you, I'm doing the calculation. You can't check. It may be any mistake. This is not a problem. So we are going to substitute this normal there to calculate the frictional force. So we are having that frictional force is equal to kinetic coefficient of friction, which is given to us and equal to 0.2 multiplied by the normal, which we did just calculated, 747.49. And then when you calculate this one, we have that the frictional force is going to be equal to 149.498 Newton. We have now the frictional force, and with the frictional force, guy, we can go back there and calculate the work done by friction, which we are going to do it real fast here on the left side. So work done by friction is equal to frictional force, which is 149.498 multiplied by the displacement, which is 8, multiplied by the cosine of 180 degrees, and the work done by frictional force is going to be equal to negative 1195.984 joules, guys. And this is the work done by the frictional force right here. So let's go to see the question. Here we are, and then that we finish. Now we have to use the work-energy theorem here to calculate the speed of the block after it has traveled the 8 meters. Is many times we practice now the work-energy theorem. And then we're going to go to a new page to do or apply the work-energy theorem for this question here. As you can see, we did many times the work-energy theorem. We're going to get a new page real fast for this question, which is question 4.3. This is question 4.3, and they ask us to calculate using the work-energy theorem, and therefore we're going to start with the net work equal to change in kinetic energy, which we state somewhere in this question or in the previous question, and we're going to apply the work-energy theorem. If we go back here to the free body diagram, which we have just here, we have that the forces are applied force, normal, weight, and frictional force. That is taking away the component and not forces. It's just a breaking down of a force. So we have that the net work is the work done by the applied force plus the work done by normal. You don't have to include the normal. It's also going to be 0 here, plus the work done by friction plus the work done by weight, which in this case is also going to be 0, is equal to half mass final speed square minus half mass initial speed square. I'm just going to take everything and move it a little bit to the left. I don't know there, and we have all the values, we have them. And then if we go back here, the work done by normal is 0, as well as the work done by weight, and the initial speed is also 0. The object did start from rest. And then all we have to do is to substitute the values we already calculated. As you can see, here is the work done by the applied forces in the question. I'm going to show you real fast. There is the work done by the applied force, 1804.21. So here we have 1804.21 minus, because the work done by friction is negative, and it is just here 1195.984, and that is the number we are going to substitute here. It is negative 1195.984, and if we substitute on this side here, the mass is 85, and then the final speed is what we are actually looking for, and the rest is just calculation, guys. And then we get that the final speed is 3,783, and this is the end of the equation. Now note that this number here at the end may have slightly different answers according to how did you round off when you calculated different questions within these questions. Guys, this is the end of the question 4 as well as the end of the video. I hope it helped. I hope you got some clarity in other questions and so on. I'll see you next time. Mr. G here. Don't forget to subscribe for the channel. See you next time. Thank you for watching.